Good afternoon, everyone. I hope you're having a good day so far. So today we're going to be focusing primarily on standing waves. This corresponds roughly to sections 16.2 and 16.3 in the textbook. So in lab these past few weeks, we've been working with standing waves kind of implicitly through videos. So we didn't get the hands-on experience that we might like to have. But if we think back to what we did yesterday in the videos Mr. Sturm shared with us, and I'll pull one up so you can see it. So we'll do a quick screen share. So if we look at the waves that he showed us, you can see that they're kind of flickering back and forth, but they look like they're staying up. So if we were to draw out that wave, it would look something like this. So it's kind of like two sine functions that are mirrored and overlap each other. This is an example of a standing wave. Now, what a standing wave is, so this is standing wave. A standing wave is a wave where the points may change amplitude, but they are not moving to the left or the right. So if you look at the videos that Mr. Sturm sent us, you'll see that they may look like they're kind of fluctuating up and down, but it doesn't look like the wave is moving in one direction or the other. So how do standing waves come to be? Well, it turns out that standing waves are the product of superposition. So we talked a little bit about superposition on Monday, and we'll talk a bit about more later today. But again, superposition is just that idea that when you have waves that meet each other, they're going to add together. So you can have two types of interference. So when waves come together, we call that interference, and it can be either constructive or destructive. So for an example of constructive interference, let's suppose we have a string and we have a square wave that's moving to the right, and we have another square wave that's moving to the left. When these two waves meet, we're going to end up with something that looks like this. It's a square wave that's now taller. So this is an example of constructive interference because the waves have come together and given us a new wave that has a bigger amplitude than the original one. Now, destructive interference might look something like this. So let's suppose we still have the one square wave that's going like this, but now our other one is flipped upside down. When these two come together, you can think if this one moves over here, since they have the same amplitude, they're just going to completely cancel each other out, and you're going to get a flat line like this. So that's an example of destructive interference, where the waves come together and they cancel each other out, at least partially. So this would be total destructive interference. You can also have destructive interference that isn't total destructive, where it just kind of lessens the amplitude. But that's an example of complete destructive interference. Now, what happens with sine functions is the same kind of idea. So let's suppose we have two sine functions that are moving toward each other. So we have a string with a sine function on it, and we have another sine function. And this one is going this way, and this one's going to go this way. Well, they're going to come together in such a way that in some cases you're going to have constructive interference, and in other cases you're going to have destructive interference, and then other situations it will be kind of in between. So it's not its max amplitude, but it's not completely canceling each other out. So so that you can see that if these two waves move to the point where our peaks are lined up, so if we have something that looks like this, so one, peaks are lined up with peaks, troughs are lined up with troughs. And it's hard to represent that by drawing on the line because they just completely overlap because they have the same amplitude. So I'm just going to show them superimposed one on top of the other. This is going to give you constructive interference because those peaks are going to add together and the troughs are going to add together. And so what you're going to end up getting is a sine function with a higher amplitude. Now, if instead we're at the point where, because our waves are going to be able to keep moving, if we get to a point, and we should have more wiggles in this one to make it actually work, like what I'm describing. But if we get to a point where the peaks line up with the troughs, we're going to have destructive interference. And so we have our one wave that looks like this. And I could draw these together on the same one because they're going to be doing the opposite thing. But just for consistency with the first constructive one, I'm going to draw it below. So we're going to have something like this. So we have a trough here and then a peak here. When they line up like that, that's going to give us total destructive interference. And at any point in between, you're going to have some kind of mix. You're going to have changing amplitudes. It's not going to be its max, it's not going to be its min, it's going to be something in between. So the way you get the the way you get the standing wave pattern that we observed in lab is by having sine waves that come together and interfere with each other. Now, before I move on, are there any questions on this so far? So you may be wondering, how are we creating this interference? Because it's not like we have both ends of our generator vibrating. You know, you have that one end that's vibrating and then the other one is a pulley attached to it, so it's just kind of hanging flat. So the way this happens, we're going to have to think back to something we talked about in the snapshots and historygraphs recitation. So remember then that I mentioned that when you have a wave and it hits a fixed end, it turns upside down. So if we have a wave, and we'll draw a square one here, but it could be a sine wave, any type of wave. And let's say that this end is fixed. So our wave is going this way. It's going to hit the fixed end, and then at some later point in time, it's going to flip upside down. So we'll draw over here. This will be our later time. Hits the fixed end, and there's some interference, and then it will kind of transition along the same as before, but upside down and moving in the opposite direction. So it's going to do something like this. What ends up happening with our generator that we see in there, so we have the generator making the sine functions, and it's actually, so you have sine functions coming in this way, they're going to hit that fixed end and reflect, and so it's actually going to be interfering with its reflection. And so that's how you're going to get that standing wave pattern, is by the interference between your incoming waves and the reflection of the waves that have already come before. So are there any questions up to this point? All right. So, let's talk about under what conditions can we have standing waves. So it turns out not every situation is going to create standing waves. So, And one thing to think to be mindful of when we're looking at the standing waves is, so when we look at our standing wave, we see something that looks kind of like this. So we have like a sine function, and then we have another sine function below. Those are two separate functions at different instances in time. So if we had two functions that were lined up like this, these would destructively interfere and cancel each other out. What you're seeing when you look at the videos that Mr. Stern filmed for us is you're seeing kind of a bunch of different waves over time. They're moving so fast that you can see both waves at once. And if you watch them in slow motion, you'll actually see that you'll only see one wave or the other at a time. You won't see both. And that little flickering stuff you see in the middle is kind of the other superpositions, or the other, you know, when they're at different, not lined up completely constructively or completely destructively. So that's why there's like those little vibrations or, you know, wiggliness in the middle. And again, if you had a slow motion camera, you could record it and you'd actually see like the individual waves. But this here thing that you see is two separate waves, and they're at that exist at different instances in time. So that's why they're not canceling each other out. It's just this one exists at some t1 and this one exists at some t2. And the difference is so small that we can see both of them at once. So are there any questions on that? Alright, so to make standing waves, it turns out that we have to have what are called nodes at the ends. So to talk about nodes, I'm going to go to the smallest number of nodes we can have and have a standing wave, which it turns out is 2. So, because you have to have nodes at either end to have a standing wave, and a node is just a place where if we were to put an xy axis on here, it would have a height of 0. So I'll draw the axis in green. So the nodes are the places where our height is 0, so y equals 0. So this is going to be a node, and this is going to be a node. And I'll put parenthetically y equals 0. So since you have to have a node at either end, the smallest number of nodes you can have and have a standing wave is 2. Now, what we call this crest here is an antinode. So the maximum point of maximum displacement, that's an antinode. And while we have 2 nodes here, we only have one antinode, because remember, this second wave pattern we see down here is actually at a different instant in time. So we're only concerned about one or the other at any given time. So we have one antinode here. Now, this half wavelength you see here, this is called the first harmonic. And it's the first because it's the smallest number of nodes you can have and still have a standing wave. So it's the first standing wave you can have. So, are there any questions up to this point? Alright, so let's suppose that our string has some length L. So our length is L. Now we have, again, just looking at this top part, we have half a wavelength here. So that string length has to be equal to 1/2 of a wavelength. So if you want to know the wavelength of the first harmonic, well, we're going to multiply both sides by 2. We're going to get that lambda is equal to to L. And I'm going to give it a little subscript 1 because this is our first harmonic. So are there any questions on that piece? All right, so now let's take a look at the second harmonic. So we can have as many nodes as we want in the middle. The key thing is we have to have nodes at either end. So the second harmonic, well, the next smallest we can have is what if we put a node right in the middle? So with this wave here, we're going to have node here, here, and here. And we're going to have 2 antinodes. And you can think about the antinodes, you can either consider them to be always the peaks that you see here, or you can imagine that you have just the one wave and make it the peak and the trough. But the key thing is that we have only 2 antinodes because realistically we only have one wave here. So this is called the second harmonic. And you'll notice that the name of the harmonic corresponds to the number of half wavelengths that you have, or the number of antinodes that you have. Now let's suppose, again, this has a length L. So we have here half a wavelength and another half of a wavelength. So we have 2 half wavelengths for a total of a whole wavelength, which means that our wavelength has to be L. So we're going to call this lambda sub 2 because it's the second harmonic, and that's equal to L. Now, let's get a little more general than this. Let's suppose now that we have M half wavelengths. So we have this, then we have a bunch of half wavelengths in the middle, and then we have this. Well, our length is still L, so we're still going to assume length as L. And now we have M number half wavelengths. So we have M half wavelengths. So if we want to know the wavelength, we're going to have to solve out for our lambda. And I'm going to give this lambda a little subscript m to denote that it corresponds to the nth harmonic. So we're going to start by multiplying both sides by 2, and we're going to get that 2L is equal to m lambda m. We want lambda by itself, so we'll divide both sides by m, and we're going to get that lambda m is equal to 2L over m, where m is going to be the number of antinodes or the number of half wavelengths. You can look at it either way, whichever one is easiest for you. So this is the number of antinodes it's also the number of half wavelengths. So are there questions up to this point? Alright, well, if we can only have certain wavelengths that are going to give us standing waves, since wavelength is related to frequency, we're also only going to have certain frequencies that will allow us to have standing waves. So if we want to figure out what frequencies are allowed, we're going to use the fact that this wave speed is equal to frequency times wavelength, and we're going to do a little bit of math. So we know V equals lambda F, and so if we want to know F, we're going to divide both sides by lambda. We're going to have F equals V over lambda. And now I'm going to give these both little subscripts for M, which is the, however many antinodes we have, however many half wavelengths we have. And we have an equation for lambda M, so we'll plug that in. So this is going to be V over, and we just said this was 2L over M. Now if you want to get this ugly fraction out of the denominator, this is the same thing as V over 1 times M over 2L, because you could rewrite the numerator as V over 1. Multiply this together and we're going to get V M over 2L. So putting this all together, we're going to have that our allowable frequencies are going to be M times V over 2L, where M is again the number of half wavelengths we have. And a key thing to note here is that M has to be an integer. So 1, 2, 3, so on and so forth. Because if M was, say, a half, well, that would mean we have half of a half wavelength, which wouldn't give us a whole, we wouldn't have nodes at either end, you'd have one node at one end potentially, but at the other end would have something that is not a node. So we have to have integers for M, we can't have anything else. So are there any questions up to this point? Alright, so the next topic we're going to talk about is we're going to go back and do a little bit of review with linear superposition and just go through an example with that. So let's suppose we have a wave that looks like this. And so our wave is gonna, let me grab a different color for our wave. Let's do purple. It's gonna have an amplitude of 1 meter for the first 2 meters. I forgot to put the label on our x-axis, but our x-axis is our displacement in meters as well. Well, displacement in meters. And then at 2 meters, it's going to drop down until it hits 0 at 3 meters. So that's a constant flat line. And so this is our t equals 0 snapshot graph. And let's suppose that here at x equals 5 meters, this is our fixed end. So what we want to know is, what will our snapshot graph look like after 3 seconds? The tricky part here is, well, we can see that I should give you a speed for this. This is moving at 1 meter per second to the right. So the tricky thing about seeing what happens 3 seconds later is this is going to hit our fixed end after 2 seconds. So it's going to hop over here, and then it's going to hop over here. And then what happens when we hit our fixed end? Well, to do this, I'm going to do this by drawing what happens after 2 seconds and then kind of moving things over. So we're going to draw our t equals 2 second snapshot graph first. So that's going to look like this. So we're still going to have the same axes. actually going to extend the x-axis a bit beyond our fixed point. So in reality, nothing exists, no part of the wave exists beyond x equals 5 meters. But we're going to bring our imaginary wave into play here, so I'm going to extend this graph for us for that purpose. So if we draw this wave, we have over here, well, it's going to have this end here is now going to be at 2, and this end here is going to be at 5. So it's going to look like this. It's going to be a constant 1 meter from 2 to 4, and then it's going to drop down like that at our fixed end. Now I'm going to go ahead and draw our imaginary wave, which is going to look like this. So it's just going to be a mirror image, but flipped upside down. So it should have an amplitude of -1 over here. So this would be our snapshot graph at t equals 2 seconds. So what we really see is just the purple curve because nothing exists past this point. But to help us conceptually figure out what happens at 3 seconds, I'm going to draw our imaginary wave, and we're going to shift both of them over by all the points on them by a meter, and then we'll be able to draw what happens after 3 seconds. So I'm going to erase our original graph. And we're going to go ahead and move each of these waves over all the points on them by 1 meter. So our purple curve, this end is now going to be over at 3 meters. It's going to have a constant amplitude of 1 meter for 2 seconds, and then it's going to drop down so that it's 0 at 6. And again, this part doesn't really exist because nothing's happening past 5. Now this red wave here, so it was at 5 here, it's going to move over to 4. So it's going to be 0 at 4, -1 at 5. And then it's going to be constant. And then it's going to drop back down to 0 at 7. Now when we do our addition, when we superimpose these two waves, we only need to worry about what happens up until 5 because what's happening over here is not really happening. So if we want to draw the snapshot graph like this, the first part is just going to be the purple curve on its own because there's no red wave there. And this time around, I'm only drawing up to 5 just to kind of remind ourselves that there's nothing happening after 5, that that's our fixed point. So we only need to worry about what's happening over here. So at 3 seconds, we go up to an amplitude of 1 meter. And that lasts until 4 seconds. Now at 4 seconds, that's where our red wave comes into play. So our red wave starts out at 0, and this is a constant 1. So this one goes from 0 to -1. This is a constant 1. So if you have 1 minus 0, well, that's going to put us at 1, which is where we were to begin with. But now, if we go from 1 plus -1, that's going to drop us down to 0 at 5. So basically this piece here is just subtracting an increasing amount from the constant number of 1, so each of these points, they're all shifted up by 1 more or less, and that's what our snapshot graph would look like for 3 seconds. So this would be snapshot for time of 3 seconds. So are there any questions on this one? Are there any questions in general? It can be on the material we covered today, the material we covered on Monday, or on this week's homework questions. Any questions at all? At this point in time, you should have basically all the material you need to do this week's homework. That Bernoulli's equation one with the pressure. The second question is a little weird, but I think Mr. Judish sent you the material from the previous chapter that you'd need to recall in order to do that one. But the snapshot, you have all the snapshot graph, history graph, standing wave information now to finish those questions. All right, well, if there are no questions, that's all I have prepared for you for today, so enjoy the rest of your day.